Hello, this presentation will cover the proposed remedy for the TH Agriculture and Nutrition Superfund site located in Albany, Georgia. I am the Remedial Project Manager, Chris Jones, and I will be walking you through this presentation. The site is located on the north side of Albany, Georgia, as noted with the yellow star on the left figure. The figure on the right shows the site, which includes 12 acres of land on 2 parcels zoned for commercial and industrial use. Before we dive into this proposed remedy for the TH Agriculture and Nutrition site, I'd like to provide some context into the Superfund process. Superfund sites are discovered when the presence of hazardous waste is made known to EPA. Once a site is identified, all existing information is reviewed and the site is inspected to determine its history and effects on the population and the environment. Information collected during the assessment phase is used to score the site according to the danger posed to human health and the environment. If a site has a high enough score and meets all other criteria, it will be placed on the National Priority List. Once on the list, the remedial investigation, or RI, begins. This involves gathering and analyzing numerous samples of soil, surface water, groundwater, and waste from locations throughout the site and near the site borders. The investigation also involves assessing risks posed by the site. Then potential cleanup alternatives are analyzed in the feasibility study, or FS. After the cleanup alternatives are developed, the option considered best for the site is proposed to the community for evaluation and comment in a proposed plan. Now, we've been at this stage before for this particular site. Back in 1993, a pump and treatment remedy was selected. Unfortunately, it was not effective and other cleanup alternatives were evaluated. A responsiveness summary of the public comments and the responses to those comments will be created once the comment period ends. Public comments can change the course of action for the site, so it's important to submit any comments you may have. The cleanup method that is ultimately selected for the site, along with the reasons for its selection, are set forth in the record of decision that will be created after the public comments have been addressed. From there, the remedy will be designed and implemented during the remedial design, or RD, and remedial action, or RA, respectively. Upon completion of the remedial action, long-term monitoring or 5-year reviews will continue until unlimited use and unrestricted exposure is achieved. Now, a little about the site background. Operations began in the mid-1950s and was used by several companies for the storage and formulation of pesticides. Thomson Hayward Chemical Company, later renamed TH Agriculture and Nutrition, or THAN, purchased the property from Planters Chemical Company in 1967. Dry formulations, which combine technical materials in a proportion specified for a particular product, was mostly done in the 1960s and 70s. The liquid formulating area was used from approximately 1973 until approximately 1978. Very little, if any, pesticide formulating occurred at the THAN parcel after 1978. THAN sold the western 7 acres, known as OU1, to Van Cleve Builders in 2015. OU1 includes soil contamination on the western parcel, where THAN operated, as well as site-wide groundwater. The eastern 5 acres, or OU2, is owned by the Jones family properties. OU2 includes soil contamination on the eastern parcel, or Jones parcel. The soil and subsurface contamination is believed to have resulted from cleaning activities. Typically, trucks were swept out on the eastern portion of the site and the yard adjacent to the large warehouse. The blending tank in the liquid formulation area was rinsed between batches of different products with xylene and was then discharged to a drainage ditch which ran east to west across the THAN parcel, behind the liquid formulation buildings to the low-lying area in the southwestern portion of the property. Before we go any further, I want to introduce some terms, the site contaminants, and how they interact with the soil and groundwater. As I mentioned, xylene was used to rinse the blending tank between batches of different products. Xylene is a volatile organic compound, or VOC, and has a density less than water, so it floats when it encounters water. The orange in this picture represents xylene and other VOCs that were used at the facility which were discharged to the ground surface. Years of this practice resulted in VOCs migrating to the soil until groundwater was encountered. Because VOCs are lighter than water, this material started to accumulate on top of the groundwater. This accumulation and pooling of VOCs continued, leading to the formation of what is termed light non-aqueous phase liquid, or LNAPL, represented by the elongated orange mass in this picture. Okay, let's continue with the site history. Business operations ceased at the site in 1982, and then conducted two removal actions to address contaminated surface soil. One in 1984 with Georgia Environmental Protection Division oversight, and the second in 1992 with EPA oversight. Activities included demolition of buildings and structures, installation of a perimeter fence, excavation of contaminated surface and shallow soil for off-site disposal, and establishment of a vegetative cover. Based on contamination discovered during the first removal action and subsequent investigations, the EPA placed the site on the Superfund Program's National Priorities List, or NPL, in March 1989. In 1992, EPA performed oversight of excavation from the top foot of soil on approximately 6 of the 7 acres on the western parcel, with specific areas excavated to 7 feet below ground surface. In total, approximately 20,000 tons of soil was removed during the second removal action. The EPA issued the OU1 Record of Decision, or ROD, in May 1993, which included the Thayen parcel and site-wide groundwater. The 1993 ROD selected pump and treat as the remedy, with quarterly monitoring and maintenance and institutional controls restricting land and groundwater use. The 1995 Explanation of Significant Differences, or ESD, expanded groundwater pumping, determined UV oxidation was not needed since the granulated activated carbon was sufficient, and added 3 dual-phase vacuum extraction wells to extract groundwater and soil gas. The 1995 ESD did not change the institutional controls or groundwater monitoring requirement. A pump and treat dual-phase vapor extraction system operated at the site between 1996 and 2002. No LNAPL was observed in the extraction system LNAPL separator during the first 2 years of operations. Therefore, EPA determined that LNAPL removal was considered ineffective, and the LNAPL separator was bypassed in November 1998. From 1996 to 2002, approximately 3.5 million gallons of water was removed, containing an estimated 480 pounds of LNAPL and 7 pounds of pesticides. In 2003, operation of the groundwater treatment system ceased due to the low contaminant of concern recovery rate. Thayen continued to monitor groundwater contamination trends and plume migration to evaluate other options for the treatment of site groundwater. In 2013, the EPA evaluated groundwater contaminant trends and plume migration and determined that the groundwater plumes were not migrating laterally. However, concentrations of some contaminants were increasing in deeper wells, likely as a result of vertical migration from the shallow aquifer zone. The LNAPL plume, or xylene, is located in the central portion of the site. The LNAPL is considered a principal threat waste. It acts as a carrier for pesticides. Therefore, this liquid contains toxic compounds and is a source of groundwater contamination. The dashed blue line represents where xylene concentrations are detected above 10,000 micrograms per liter. Monitoring well MW-N2 regularly contains measurable LNAPL. In October 2022, it was measured at a thickness of approximately 2.5 feet. Similar to the xylene plume, the toxaphene plume is located in the central portion of the site, but also extends onto the western side of the Jones parcel. The dashed magenta line represents where toxaphene concentrations were detected above 3 micrograms per liter. The highest toxaphene concentrations were observed in and around MW-N2, which regularly contains measurable LNAPL. This slide is going to touch on the chemicals of concern and cleanup levels, which are based on either Safe Drinking Water Act maximum contaminant level, referred to as MCLs, or human health risk-based values. Let me try to provide some context on these values. MCLs are laws that help ensure our drinking water is safe to consume. Each chemical-specific value is based on scientific research and health considerations. Human health risk-based numbers are important tools for assessing the potential risk associated with exposure to various substances. These numbers are based on scientific data and are designed to ensure that people are not exposed to harmful levels of toxic substances in their daily lives or work environments. The units of measurement for the proposed cleanup goal are micrograms per liter. This measurement expresses the concentration of a substance in a liquid or solution. Specifically, it refers to the number of micrograms of a substance, in this case, a contaminant, which is present in 1 liter of liquid. This is a very small number. Take, for instance, a dime, a raisin, or one plain M&M, and imagine holding it in your hand. Each one of these weighs about 1 gram. If you were to cut an M&M into 1 million pieces and dissolve one of those pieces into 1 liter of water, you would have 1 microgram per liter of M&Ms present in that water sample. Now that we have a basic understanding of how cleanup numbers are derived and the units used to measure them, let's continue. With the exception of xylene, the 1993 Record of Decision, or ROD, listed these chemicals of concern and associated cleanup targets in the middle column. This amended ROD will not change the cleanup level for EDB and toxaphene, since those values are still the current MCL for those contaminants. This amendment will add xylene as a chemical of concern with a preliminary remediation goal of 10,000 micrograms per liter, which is the MCL for that chemical. It will also decrease the remaining pesticide chemicals of concern identified in the yellow box to an acceptable risk. Achieving these preliminary remediation goals would meet EPA's upper bound of the acceptable cumulative risk range and the non-cancer hazard index of 1.0 for both residential and worker exposures. These next 2 slides will look at the alternatives evaluated for LNAPL and non-LNAPL groundwater. Because we have LNAPL, which acts as a carrier for pesticides, we are looking to address the LNAPL first, then the non-LNAPL groundwater plume or pesticides. LNAPL alternative 1 is the no action alternative, which is evaluated at all Superfund sites as a baseline for comparative analysis purposes. LNAPL alternative 2, in situ chemical reduction and enhanced anaerobic biodegradation, injects amendments to chemically degrade contaminants within the LNAPL area. Performance monitoring would be necessary to confirm long-term reactivity and effectiveness. LNAPL alternative 3, air sparging, includes installation of air injection and vapor extraction wells throughout the LNAPL area. VOC emissions would be captured with devices such as granulated activated carbon. The system would be operated for at least 2 years, during which groundwater performance monitoring would occur to maintain system optimization. LNAPL alternative 4, thermal treatment, includes installation of thermal conductive heating wells throughout the LNAPL area. Thermal conductive heating is used to heat the subsurface to volatilize the chemicals of concern. Soil vapor extraction wells would be installed to capture vapors generated during thermal treatment. Regarding the non-LNAPL groundwater alternatives, alternative 1 would include no further action. Non-LNAPL groundwater alternative 2, monitored natural attenuation, includes monitored natural attenuation, or M&A, of chemicals of concerns in groundwater rather than active remediation. Chemicals of concern concentrations would be monitored to confirm stable or shrinking plume and continued decreases towards groundwater cleanup levels. Non-LNAPL groundwater alternative 3, in situ chemical reduction and enhanced anaerobic biodegradation. As previously mentioned, it would include injection of amendments to chemically degrade chemicals of concern, and performance monitoring would be necessary to confirm long-term reactivity and effectiveness. The costs of the discussed groundwater remedial alternatives are shown here. The costs range from $0 for the no action alternative to $14 million for the thermal treatment. The alternative that is being proposed to address the contamination on site is air sparging with soil vapor extraction for the LNAPL and in situ chemical reduction and enhanced anaerobic biodegradation for the non-LNAPL groundwater or pesticide plume, which comes in with a combined total around $8.78 million. Elimination of the principal threat waste, which is the LNAPL plume containing toxic compounds, is needed to help immobilize the non-LNAPL groundwater contaminants. After evaluating all alternatives against the criteria, the preferred remedy for operable Unit 1 is a two-phased approach due to one remedy injecting air and the other requiring an anaerobic or no oxygen environment. First, eliminate the LNAPL with a proven technology, air sparge with soil vapor extraction. This will remove the source or the principal threat waste and help further reduce the likelihood of pesticide vertical and lateral migration. The system would be operated for at least 2 years, during which groundwater performance monitoring and influent soil vapor extraction vapor sampling would be conducted to assess remediation progress and to support system adjustments and optimization. Phase 2 will utilize in situ chemical reduction and enhanced anaerobic biodegradation on the pesticide plume to speed up the breakdown of these chemicals. Performance monitoring will be conducted to confirm long-term reactivity and effectiveness. It should be noted that while injections would accelerate groundwater contaminant of concern concentration reductions, achieving groundwater cleanup levels would likely require several years of post-injection groundwater monitoring. Let's take a closer look at how these remedies will work. As I mentioned, air sparging with soil vapor extraction will be the first phase, which will primarily address the LNAPL plume. The combination of air sparging with soil vapor extraction helps to remove contaminants from both the soil and groundwater by promoting the transfer of these contaminants from the soil and water into the air, then capturing and treating the contaminated air. So how does it accomplish this? Air sparging injects air into the contaminated groundwater or soil. The air rises through the water or soil, creating bubbles that strip contaminants from the water or soil and transfers it into the air. This process helps to release volatile organic compounds and other contaminants from the groundwater or soil into the air. The air, now carrying the contaminants in the form of vapor, is then extracted from the soil or groundwater using a vacuum or blower system called soil vapor extraction. The air is pulled out of the ground or pumped out from wells, and it passes through treatment systems to remove or capture the contaminants from the air before it's released into the atmosphere. The second phase will involve in situ chemical reduction and enhanced anaerobic biodegradation. This is a process that uses chemicals to change the contaminants into forms that can more easily be broken down by microorganisms in an environment without oxygen. This is accomplished by injecting a mixture of nutrients and zero-valent iron, or ZVI, into the contaminated groundwater or soil. The nutrients provide food, and it promotes a friendly environment for bacteria needed to help break down contaminants into less toxic forms. Zero-valent iron is a type of iron that has lost all of its positive or negative charges and does not have any chemical bonds. This makes ZVI highly reactive when it comes into contact with chlorinated solvents, heavy metals, and other organic and inorganic pollutants. This chemical reaction reduces or transforms these contaminants into less toxic or less mobile forms, and it also acts as a catalyst to promote degradation of organic compounds. This concludes the technical components of the proposed remedy for the TH Agriculture and Nutrition site. I hope you have a better understanding of the Superfund process and how we intend to implement the proposed remedy for the site. The public comment period will run from May 10th to June 9th. All comments can be submitted to me at jones.christopher@epa.gov or mailed before June 9th to the US EPA regional office address provided here. The site's administrative record, which contains all site documents such as the remedial investigation and feasibility report, is available at the site's webpage listed here. The EPA will provide the opportunity for a live virtual meeting if the community requests one. For any questions, feel free to reach out to either me or the Community Involvement Coordinators Marjorie Thomas or Donica Wiley at the emails or phone numbers provided. After EPA has received comments and questions during the public comment period, EPA will summarize the comments and provide responses to all questions and comments in the responsiveness summary, which will be part of the amended record of decision, or AROD. The AROD will select the final remedial action and will provide the rationale for EPA's selection. The AROD will be available for review in the information repository and online once complete. Thank you.